Alrighty, here's the second half of Unit 2, Lesson 15, when we're looking at a study of remainders. So we just learned that when we do some division, polynomial division, sometimes it'll divide in evenly and sometimes it won't. And we'll have a remainder. So we get this question, where it gives us all of these polynomials and it wants to know, is x minus 2 a factor of each one? And it doesn't give us a whole lot of space. So I'm kind of already thinking there's got to be some other way to do this that's going to take up a little bit less room than doing polynomial division 6 times over to see if it has a remainder or not. So there are times where we don't really care about what the whole result is. We don't care as much about what our answer is, only whether something is a factor or not. Meaning, does it have a remainder or not? So we want to come back to that meaning of what factor is. If x minus 2 is a factor of a polynomial, this x minus 2 factor turned into a 0 of the graph. Remember how we did this in lesson 5, I think it was. We took every factor and we set it equal to 0, and then we solved until we got x equals. So in this case, it's just adding 2 to both sides. And we saw how this is a 0 of the graph. It gave us an ordered pair. Input 2, output 0. So this is making this idea that if it is a factor, if x equals 2 is an x-intercept, it should be giving us an output of 0. So if we use that idea with each of these, I don't have to actually divide the factor into each one of them and see if it goes evenly or not. I can try this input, so our steps of what we're doing to make this happen. And if we just want to test any factor, we're going to say this: to test a factor. It's a 2-step process. 1, turn the factor, and I'm going to put that in quotes because it's I don't know if it's really a factor or not, into x equals. Whatever it takes to get that to an x equals. In this case, all I had to do was add 2. Sometimes I may need to divide by another number or do something more, but we want to turn that factor into an x equals. And then our step 2 is to plug it into the equation. We're going to find our output. And I only care if that output is a 0 or isn't a 0. What number it is less important to me. If that output equals 0, then we're going to say yes, it's a factor. If it doesn't equal 0, meaning if it equals anything else but 0, it is no, not a factor. So instead of doing polynomial division 6 times over, in this case, if I'm testing what my output is when x equals 2, I'm just going to plug that into my equation and I'm going to solve for it. So I'm going to find a of 2. I'm going to see what its output is. Now I'm just going to go calculator crazy on this, all right? Because I don't feel like even doing that much math. And I just want to remind you about things like putting your input in parentheses in case this is like if a factor starts with x plus 2, and we're putting in a negative 2 and testing that we get in that habit that we put in a negative sign inside the parentheses, close parentheses, then use an exponent because, yeah, that's going to give us a different value at different times. So I put into my equation, I calculated the output is 5. 5 does not equal 0, so this is not a factor. So I'm going to put no, not a factor there. What this has told me is that I have a point on this graph of 2, input of 2, output of 5. Now that is not an x-intercept. It's not a 0 of the graph. It's not a solution. It's none of that stuff. So it is not a factor. Keep on trying this. I'm going to find b of 2. And I'm just writing out these first couple ones. I do always want to write down what the output is. Ooh, this one equals 0. So I'm going to say this one has a point at 2, 0. That is a 0 of the graph. And I'm going to say, yes, this is a factor. If I divided, it would have a remainder of 0. C of 2, when I plug it in, I'm not going to write out the whole thing, but I am going to, get it into my calculator. I'm going to keep track of what my answer was. 13(2) squared. Double check that I typed that in right. Enter. 105. No. Not a factor. Sorry. Double check that you know how to type all these in and you're getting that same answer that I am, because there is amazing things that happen when you have calculators in someone else's hands compared to our own hands. So for each of these, I turned the factor I'm testing into a 0, into an x equals. I took that x equals that value and I plugged it into the equation and I found the output. And only if the output was 0 did I say, yes, I have a factor. And when my output was anything other than 0, like 5 or 125 or negative 324, doesn't matter what that number is, that it tells us that it's not a factor. So I just want to test one of these and kind of show you another example of polynomial division with a remainder. So there's this really cool thing that we can make a connection here. Each of these things up here, if we were able to put them in here as a ordered pair and tell which one was the factor or not. This 0 actually also tells us the remainder if we had done division. So not only are we coming out of this with an ordered pair like 2, 5, or 2, 105, or 2, negative 324, we can also say that if we tried using division, that we can tell what our remainder would be. Here in part B, it asks us to do that. It asks us to divide one of our polynomials by x minus 2 to show the remainder of what it is. Now, I'm going to pick C, okay? So I'm going to use C for all of my ideas down below. It says to select one of your polynomials that you said doesn't have x minus 2 as a factor. C does not. We know it's not a factor because when we plugged in positive 2, what we suspected to be a 0 of the graph, the output was not 0, so it's not an x-intercept. So we're going to try dividing that because I want to just have one more practice here from scratch of dividing something with a remainder. So 2x to the third plus 13x squared plus 16x plus 5 divided by x minus 2. So I copied that polynomial from up here, and I'm checking this x minus 2. All right. We're going to do our standard setup for polynomial division using the grids. We put the factor that we're checking on the outside. I don't know how many columns it's going to be. I put my first leading term into the first inside box, 2x to the third. There's my setup. Now I start working my polynomial division. X times something to get to 2x to the third. Well, I need a 2. And I need 2 more x's. I need another x squared here. Okay, once I have something on the top, I can fill it all the way down. 2x squared times a negative 2 would be a negative 4x squared. I don't know what's in the next diagonal box, but I know my 2x squared terms have to add up to and equal 13x squared. So we multiply into the boxes, we add to get out. Negative 4 plus something has to get to positive 13. So that's going to have to be a positive 17x squareds. Repeat that division again. Now we're ready to start a new column. X times something to get to 17x squared. It's a 17, positive 17. I need one more x so I can get to that x squared in here. So plus 17x goes up there. When I know the top of a column, I know the whole column all the way down. 17x times a negative 2 is a negative 34x. I'm going to keep going because I don't have a constant up here on the top yet. So I'm going to keep on going. That might be a nice signal to you to know when you're done. X squared, x to the first, x to the 0. I'm going to have one more column here with a constant. I need to get to 16x. It's a positive 16x. I'm at negative 34. So I need to go 34 to get to 0, and then 16 more than that. That is positive 50 x's. X times something to get to positive 50x. That's got to be a 50. Positive 50 times a negative 2 is negative 100. Now I've got my constant there, so I know that's the end of my grid. But it's not the end of my problem because I have to get that plus something to equal a positive 5. I'm at negative 100. I need to get to positive 5. This means I need to add a whole bunch. I need to add 105. So when I did this division, I got a result of 2x squared plus 17x plus 50 with a remainder of 105. The remainder equals 105. That's what my question was. What is the remainder? It's 105. And then our next question says, how do the values compare with our functions when x equals 2? That is asking me to make this connection right here. That this remainder, when I did the polynomial division, is the same as the output that I did up above. So if I need the whole result, I'm going to have to do polynomial division. If I need to know whether it's just a factor or not, or I just need the remainder, I could just turn it into an x value, plug it in, and find out the output. So that's a pretty cool problem right there. Pretty neat to see we have a faster way to check if something is a factor or not, and then we can still find the remainder either way. Now I want to go that extra mile and look at the lesson 15 cool down. So if you have a cool down packet and you've got this one, it asks us in kind of an interesting kind of way some information. We have a polynomial function. It's a third degree polynomial. And ultimately my task is to write it as a product of linear factors. Okay, p of x. Here's my task and how I know when I'll be done. I have a third degree polynomial. I need 3 linear factors. They give us a bunch of ordered pairs, essentially. Okay, we were writing them like that here. D of 2 equals 0, C of 2 equaled 105. They're doing that same thing here. So P at negative 4 equals negative 33. If that is not a 0, that's not an x-intercept. That means this is not a factor, so I don't care at all. I don't care about that. That's not helpful for me to write any factors that I have here. This next one, though, is so helpful because when I plug in negative 3 as an x, I get a 0 out. I'm going to take that over here and think about this, that if x equals negative 3, I get an output of 0, I have a 0 of the graph. That 0 turned into a factor. Remember how to do this. Factors are equal to 0, so I have x equals negative 3. I need to push that negative 3 over to the other side to get it equal to 0. X plus 3 equals 0. There's my first factor. When I plug in negative 2, I get out 7. I don't care one bit about that. That doesn't help me write a factor. This one does help me write a factor. When x equals negative 1, turn that into a factor. There's my second factor. And I could use polynomial division. I could divide this by one of our known factors, then divide that answer by our other known factor. I'm looking for my third one. But remember, there's a faster way that we can use to speed this up. If all I'm missing is one factor, remember that all of our x terms have to multiply to our leading term there in our standard form. So x times something has to get us to 2x to the third. I need a 2 and I need an x, because x times 2x is 2x to the third. And similarly, positive 3 times positive 1 times something has to equal negative 9. 3 times 1 times something, we're kind of back to those boxes from a couple lessons ago, has to equal negative 9. 3 times 1 is 3. 3 times negative 3 is negative 9. Let's put a negative 3 in there. We found our missing factor. We wrote all of our linear factors. So some cool stuff can start to happen when they give us a couple known values, especially if they give us a couple known zeros. And we can find linear factors in that way. All right, go try lesson 15 practice problems. Good luck, y'all.